I decided to build social learning system on several tiny neural networks. Why? Because we, human beings, learn socially. We copy the best discoveries and practices from our entourage. Of course, we not only borrow, but also seek out new knowledge through trials and errors. And sometimes we resort to thoughtless copying. Cloning does not happen entirely due to copying errors, but also due to adaptation to the environment and the combination with already known knowledge. How can we use all of that in the artificial intelligence and machine learning? And I thought, I can make some experiments. Imagine 4 hunters search food in the forest. They're all quite similar, but differ a little bit in their temperament or speed. Some of them search carefully but slowly. Others prefer run quickly across the territory. Sometimes they shout to each other and find out who has made more progress toward the goal. They come together and start their search again from the best intermediate point. And now, from the metaphor to the present. I built 4 small models, only 3 layers. 1 input, 1 output, and 20 hidden units plus a ReLU function. Without this newfangled correct activation, layer normalization, fancy dropouts, etc. But each network has a different learning rate, which distinguishes a lot. Why 4? 4 is a small group with a close interaction, and most importantly, 4 is the size of the person's fast memory, according to research. Anyway, it's actually a hyperparameter. Neural networks are trained sequentially. It's possible to do it in parallel, but I have only 1 GPU and no technical abilities. The last functions are compared every n epochs, and all models clone the dictionary of parameters from the network with the lowest loss. This cycle is called a big epoch. For comparative analysis, I use the same network but only 1. And of course, 4 is better than 1. So model is trained 4 times as many epochs. And then the training time will be approximately the same. The training was on relatively complex data. Can't just draw a line. And I also made a comparison with the different computational budgets. And what do we have? All networks showed relatively normal results. But in a shorter amount of time, a group of networks functions better. Then I took more sophisticated data, and here results are worse. The simple ordinary model with the biggest budget for training won. What if the frequency of information exchange is very important? With dense communication, we try to prevent individual hunters from galloping away from the path of learning, and they explore the space of losses locally. But with the rare conversation, you can learn much more. I tested different exchange frequencies between networks, and here things get a lot more fun. I added swaps for weights every 10,000 epochs. On relatively simple data, hunter groups are in the 2nd, 3rd and further places by effectiveness. On hard data, the model with exchanges once every 1,000 epochs and with the largest training budget is the best. When exchanging once every 10 epochs, there is a high chance of falling into a local minimum trap, from which there is no way to escape. By the way, ADMW optimizer is terrible in its social learning. Let's expand a little the research and add more frequencies to the parameter swap. For example, every 2000, 4000 and 10,000 epochs. Simple data show a primacy of fast talks between models, although many groups of social learners dominate the single model. On complex data, relatively rare exchanges perform better. But maybe it's coincidence. I studied this question in more details using hard data. I conducted 10 training for each of the options. It's not exactly scientific, but still the best expectation is for exchanges once every 2000 epochs. Summing up, social learners with relatively long delays between parameters exchanges are better than single model in a constant training budget. Then I made a graph like this of the effectiveness of the model roll calls. You noticed I didn't show the test loss, as they don't always provide adequate estimates of the model, especially when we know how the function is evolving. I marked the model that understood or guessed how the data would behave in other points. Only the best several models have rank 1, and all other are in rank 0. And it turns like this. The overall picture does not vary, and it even strengthens our conclusions. Groups of models learn better for a given budget of calculation. But the frequency of information exchanges remains questionable, although on simple data all cases of exchanges cope one way or another. But on complex situations it's better to exchange parameters more rarely. And by the way, in all the possible launches, only models with social learning achieved an understanding of the future development of data function. Although all this raises the question of the effectiveness of training in general for prognostic goals. It seems that this whole joint system of model training represents a form of a more complex scheme of adjusting the learning rate. Standard methods of the learning rate tuning are either a simple function of time or depend on the dynamic of losses. We get is more broken curve and not a continuous function for decay. Finally, given the time constraints, the social model is simply better. It's worth testing and trying on other data and networks.